Carbon nanotubes are rolled up sheets of graphene with amazing mechanical, thermal, and electrical properties.
Well, CNTs are very simple. They are carbon atoms arranged in a molecule form. The black things in here in this model is a carbon atom. The transparent tubings represents carbon bonds, so they form 6-member rings of carbons, and they roll up in a tube like this. And it's one of the bigger molecules you can find.
Today we're going to look at some carbon nanotubes under scanning electron microscope.
Carbon nanotubes are nanocylinders, so then the question would be, what would be the diameter of the nanocylinder?
Now let's load the sample into the SEM chamber.
So typically, for example, for the carbon nanotubes that we grow in our lab, the diameter would be maybe 1.2 up to around maybe 1.5 nanometers.
We'll raise the height to a height that's appropriate for imaging.
For example, if you draw a long line, which is a meter long, and now you split up that line into billion equal parts, the length of one of those parts would be 1 nanometer.
The samples that we'll look at have carbon nanotubes that are single-walled and semiconducting, grown horizontally and in a line fashion. It's a ring of carbon that is 1 to 2 nanometers wide, and it can extend up to 1 millimeter long, so it's 1 million times longer than it is wide. And because of this unique property, they're very useful for applications in electronics.
CNTs are exciting because if you can build transistors and logic and digital systems out of the CNTs, you should be able to produce this really high performance information technology systems. You should be able to run that system out of a tiny little battery.
Yeah, with carbon nanotube, it's a very special material. So we want to use them to make things that are not possible with other materials, or enable new devices or new technologies where nanotube can allow much better performance.
Depending on how a sheet of graphene rolls into a carbon nanocylinder, that determines the electrical properties of that carbon nanotube. Sometimes you could have carbon nanotubes that are semiconducting, which you would use for transistors, or they could be metallic. Those would be terrific for wires, but they are not very good as transistors. When you grow these carbon nanotubes at a very large scale, it's extremely difficult to control that all your carbon nanotubes would be perfectly semiconducting.
I work on demonstrating that we can experimentally build working, larger scale, useful circuits out of carbon nanotube transistors. Carbon nanotube circuits promise both increased energy efficiency and performance. However, there are many obstacles towards realizing a working carbon nanotube circuit. Now, many of these obstacles are inherent with the carbon nanotubes themselves, such as the mispositioned and the metallic carbon nanotubes. Our group here at Stanford has come up with many techniques, some based on how we design the circuits, some based on fabrication techniques, which overcome these inherent imperfections. By overcoming these inherent imperfections, and by developing robust fabrication techniques specifically for carbon nanotubes, we're able to demonstrate for the first time some larger scale useful circuits using carbon nanotubes. Now, I'll show you two of the more recent circuits we've built using carbon nanotube transistors. Meet Cedric, the carbon nanotube digital integrated circuit. Cedric is the first computer built entirely using carbon nanotube transistors. Cedric is a very basic computer which runs a basic operating system, which is capable of multitasking. For instance, right now, Cedric is both sorting and counting numbers concurrently. Cedric is composed of tens of thousands of carbon nanotubes, showing that we can actually fabricate carbon nanotube circuits in a scalable and manufacturable manner. And meet Sasha, the Stanford carbon nanotube controlled handshaking robot. Sasha is controlled by circuits fabricated completely using carbon nanotube transistors, and is the first complete subsystem built entirely using carbon nanotube FETs. Now, let's take a look and see how these carbon nanotube transistor circuits are made. It all begins in this lab, where we grow our highly aligned carbon nanotubes on our quartz wafers. We put the quartz wafer into the furnace, and after several hours, get our grown carbon nanotubes.
Then you pass or flow gases that contain carbon atoms, such as methane and so on. And on the substrate, you would put catalysts, such as iron or cobalt, metal catalysts, and carbon nanotubes would then grow from these catalysts, getting carbon from the environment where you feed the carbon gas in.
After growing the carbon nanotubes on the quartz substrate, we then transfer these carbon nanotubes onto a traditional silicon dioxide substrate using a low-temperature transfer process. This renders the entire process silicon CMOS compatible. CMOS circuits are one of the fastest and most energy-efficient designs currently in use. We are working to use CNTs in CMOS circuits in place of silicon. One of the challenges is transforming the CNTs by doping them with other materials.
I'm working on understanding the physics behind carbon nanotube transistors. In order to realize energy-efficient transistors in future using carbon nanotubes, we have to come up with complementary logic. In order to realize complementary logic, we should have PMOS and NMOS transistors using carbon nanotubes. Now, it is very easy to realize PMOS transistors with carbon nanotubes, but realizing NMOS transistors is somewhat of a challenge. I'm working on trying to understand the mechanisms behind carbon nanotube doping techniques so that we can realize N-type transistors in future. Hopefully, as we keep on refining the carbon nanotube doping techniques, we can make even better, faster, and more energy-efficient circuits in future.
We have also been able to demonstrate in our group monolithically integrated three-dimensional circuits using carbon nanotube field effect transistors. Now, it's very difficult to build such monolithic 3D integrated circuits using silicon transistors, because once you fabricate silicon transistors in the upper layers, the circuits in the lower layers, they could get damaged. But with carbon nanotube field effect transistors, it's very cool that in the lab, you can build these three-dimensional integrated circuits very easily. And that opens up great opportunities for new generations of circuits and systems that can perform massive amounts of computation in an energy-efficient manner.
And I'm building a skyscraper in the world of carbon nanotubes. Think of one single transistor as one person. Today's integrated circuits are like the Quincy Market in Boston, where all the vendors and customers are crowded into one single story, and it can be extremely difficult for you to move from one end to another. We can make tomorrow's electronic systems skyscrapers where we have multiple stories on top of each other, so that more people can work together and collaborate more effectively. While people are trying really hard to push the physical limits of the transistor scaling, carbon nanotube 3D integrated circuits manifest themselves as a brand new interpretation of the traditional concept of scaling.
We're making touch sensors more sensitive. We're making electrodes that are stretchable. With carbon nanotubes, we're making energy-generating devices using them. Also, we're making transistors that are flexible and potentially printable over a large area so that we can use these transistors to power the displays we're using for laptops.
So here we have our carbon nanotube ink, and here we have our substrate with a metallic stencil on top, through which we're going to deposit our carbon nanotube ink. And as you can see,
I can take it off now. I just remove the vacuum, and then I can take the substrate. After we spin coat the nanotubes on top of the circuit, we can take the flexible substrate off, like so. And we can use them for flexible display, or we can put them to RFID circuit.
To align the carbon nanotubes, one of the ways to do that, especially over a large area, is to use a liquid to flow the nanotube across the substrate. This is kind of like flowing logs along the river. Then these logs will be aligned along the direction of the flow of the river. So this kind of phenomenon can actually be applied to align carbon nanotubes over a very large area without using sophisticated methods.
What needs to be done is certainly to make it more of these in a large scale and make sure they are reliable and yield properly and has the right performance in terms of energy consumption and speed that we expect it to have from our modeling studies. And what is the physical process of information being retrieved, the energy being consumed during that process, and how fast these data come to your computer or to your cell phone. All these are based on a physical infrastructure that is made of basic electronic systems. From a technical point of view, there are a lot of things such as doping, contacts, scaling down the small device size and feature sizes, all these kind of the technical details of making a real technology work.
I'm working on graphene, which is related to carbon nanotube. I'm using it as a copper diffusion barrier. Copper is widely used as circuit wires, but it can move around through diffusion. So we need to use another layer of diffusion barrier to keep it in place. So we are using graphene instead of titanium nitride because graphene is super thin while maintaining the barrier property, so that we can make even smaller and smaller circuits.
My research project is directed self-assembly of block polymers. Nowadays, people use photolithography to print those lines and features of integrated circuits. But as all the electronic devices are becoming smaller and smaller, it's reaching the limitation of photolithography. As an alternative approach, we're using those polymers to rearrange themselves to form those tiny nanostructures.
Our strategy is what I call imperfection immune design. So you use new design techniques that work hand in hand with processing and materials so that when you finally build your digital system, those digital systems are immune to any of the imperfections that you might incur when you are doing the processing and the growth of the carbon nanotubes. If we have this a few levels deep understanding of how the basic technology works, then we can come up with clever tricks when you design your circuit blocks in such a way that when you lay them out on top of the carbon nanotubes, you can even mathematically prove that the way you do the circuit designs, still you will guarantee correct logic functionality of the digital system. And the key point is, you can do that at negligible costs.
These are the current voltage characteristics in a carbon nanotube transistor, and the circles are the experimental data. So the lines are the model we built, so we can see if the model agrees well with the experiments. And a good model is very important because it enables us to run circuit level simulations, and we can predict the performance, the potential benefit we can get from carbon nanotube.
My job is to figure out exactly what needs to be done in order to make a computer chip that has 1 billion of our carbon nanotube transistors. The problem is that making 1 billion of anything isn't easy. Not even all of the transistors will be the same, and definitely not all of them will work. Even if we have a 99.99% chance of making a transistor that works, that's still 10,000 out of a billion that won't work, and so our full computer chip will fail. I look at all the things that can go wrong with carbon nanotube transistors and then figure out which aspects of the transistor need to be improved the most. For example, if you look at the CNTs here, you'll see that there is not exactly the same spacing between every carbon nanotube. So I'm like the middleman between the people that build the computer chips and the people that build the individual carbon nanotube transistors. I figure out all the specifications that need to be met at the transistor level, such as the exact size and shape of the individual transistors and the limits on the spacing between the carbon nanotubes.
These circuit designs are so efficient that at a large digital system level, there is almost no additional costs in terms of power, performance, energy, or area that you have to incur to be able to create these systems that are immune to these inherent imperfections at the carbon nanotube level. And that's where there are opportunities for great innovations that we are working on.